Yeah.
Merry Christmas, welcome back. We are filming this over Christmas break, so here we go. So I'm gonna have you guys start off with the momentum pretest. Answer these questions, do the best you can. I don't expect you to know how to do them. If you don't know, make something up. Funnier is better. What is momentum? How can you change how much momentum something has? Why are cars made with bumpers that crumple in a crash? What is the best way to take a punch to the face?
You can't avoid it. It's coming in. What are you going to do? Don't
How
look
do you
this
do
up in
that?
the book. See, just make something up if you have no idea.
What's a book? No. Just make something up. Do the best you can. I want to see what you know. Okay. So momentum is inertia in motion. It is a vector quantity, which means it has a magnitude and a direction.
Yeah. Symbolized by the letter P, lowercase p. Don't ask me why.
It is what it is. Momentum. This is the equation that you're going to use. P equals m times v, where m is mass in kilograms and v is velocity in meters per second. Here are our units, and you know what? This is actually really important. We're going to be coming back to these units later. Kilogram meters per second or a Newton second. These are the same thing.
Look how simple that equation is. Just how much mass you got times how fast it's going. That's all momentum is. It's simple.
Could you have momentum? Oh, here we go. 65 kilogram Miss Moore walks at 2.4 meters per second. How much momentum does she have? Okay, well, momentum is mass times velocity, and I am 65 kilograms of mass, and my velocity is 2.4 meters per second. Isn't this easy?
I think so.
This is pretty easy. Look at that. Okay, so 65 times 2.4, and I get 156.
156 what?
Kilograms meters per second, or we can call this 156 Newton seconds.
Okay.
Okay,
See how simple that is?
Newton seconds. That's right? Newton seconds? Yeah.
Yeah.
Because they cancel. Okay, so how much momentum do I have? 156 kilogram meter per second or Newton seconds. Okay, how can a 3.7 kilogram bowling ball have the same momentum as a 0.34 kilogram softball?
How can it have the same momentum?
Okay.
What is momentum?
Well, momentum is mass times velocity, right?
You got two things to play with. Which one has more mass?
Well, our bowling ball is going to have a big mass,
Yeah.
okay? And it has to multiply by velocity, right?
Sure.
And our, what was it, a softball?
Softball.
Our softball is going to have a little mass, but they both have to have the same momentum, so check this out. It's just going to have more velocity.
That could be 10 times 2 and 2 times 10.
So this is a bowling ball, this is my softball. And just like Mr. Boykin said, this could be like 10 times 2 or 2 times 10.
They both
Right.
equal 20.
Bigger mass, lower velocity, less mass, faster velocity, more velocity.
Let's give them a chance to do one out of the book.
Okay, so we're going to take a look at 204, page 204. And it says number 1. We're going to do this underneath the thing. A compact car with a mass of 725 kilograms is moving at 27.8 meters per second. You're welcome.
Yeah.
Towards the east. Sketch the moving car. Let me sketch first.
Toward the east? What is east? Oh, that's the direct. And then it says find the magnitude and direction of its momentum.
Okay, so we want to find the momentum. Okay, so we've got our car right here, right?
Yep. The
And-
mass is 725 kilograms.
Okay, and the velocity is
27.8 meters per second.
meters per second, and it's going east.
Yeah, east.
Okay, we're gonna east is that way.
Yeah.
Okay, well technically it's that way, but anyways, on the board it's that way. And we want to figure out what the momentum is, right?
Yeah.
Okay, momentum is mass times velocity. 27.8 meters per second. I flipped these, but whatever, you know. Velocity here times the mass. 725 kilograms.
Put the answer over there.
Oh yeah. 27.8 times 725, and I get, that's a big number. 20,155. My kilograms, meters per second. Again, this could also be a Newton
But
second.
yeah.
But we won't.
See how simple that is?
It's easy, right?
Yeah. Is that the end of it?
Find them. Oh, I forgot the direction.
Oh.
It's gonna be that way, which is east. Because it's a
See,
vector.
'cause you had the direction here. It should go in here as well.
Yeah, one has more. Don't be like this more. Include your direction. Okay. And then a second car, mass of that many kilograms, has the same momentum. What is its velocity?
Do this over on the left.
Yeah, I'm gonna do this right here.
So it's got the same momentum, so it's going to be 20,155.
Momentum equals mass times velocity. What was the mass of this guy?
2175 kilograms.
Okay, so at first I was like, okay, where do I start with this? But it has the same momentum, you say, right?
Yeah, so we know what the momentum is. How do you solve for the velocity?
Meters per second. Well, we can just divide by the mass.
Yeah, and that's east.
East.
Well,
Okay. Velocity is gonna be, That means our answer is gonna be east. Let's do these cancel. Velocity equals momentum over mass. My momentum was
20,155 kilograms meters per second east.
east over
2175.
21. Velocity is gonna be some number east. Okay, so do I have that number in there? I sure do. So just divide it by 2175, and I get 9.27.
So that's a smaller velocity.
Sorry. 9.27. 9.27 meters per second.
East.
Boom, boom. East.
That sure is simple, Miss Mo.
I know, it's easy, right? Just use mass times velocity and draw out your diagram. It helps.
They both had the same mass. I beg your pardon, same momentum. Larger mass, small velocity. Smaller mass, large velocity.
Yeah. This one has less velocity. This one has more velocity. This one has less mass, more mass. Okay. All right. Oh wait, go back there real quick. Do we need to go? No, we're good. Oh, wrong way. Wrong way. There. We just did this one, right?
Yes.
Okay. When the momentum of a bowling ball changes, what changes?
Here's a bowling ball.
Here's a bowling ball. Look at this, a bowling ball out here in
What's its momentum?
the wild. Well, right now it has a momentum of
0.
0. Okay. So when the momentum of the bowling ball changes, what changes?
Oh, it's got momentum now.
What? Okay. And now it's stopped again.
But what about the bowling ball change that when its momentum changed?
Okay. So this is harder than it looks.
I know.
Get on the hole there. So when the momentum of the bowling ball changed, it's because I kicked the ball. Right?
Yeah.
I applied a force. Now, is
But
the mass of the bowling ball changing?
Nope.
So what's changing?
The velocity.
The velocity, right? So I kick the bowling ball. Okay, I apply a force. I kick the bowling ball, and the mass is the same, but the velocity changes. Now again, I apply a force here.
The momentum goes back to 0.
The mass hasn't changed. It's just the velocity.
That's simple.
So when momentum changes, it's only because the velocity is changing. And here we are, more equations, woohoo! Okay, so the change in momentum, it equals mass times the change in velocity.
Yeah, this is a simple thing on top. It just tells you when the momentum changes, it's the velocity that changes.
Yeah, we just talked about that, right? With the bowling ball. And whenever you see this delta, this change sign, that really just means, as always, final minus initial.
Final momentum minus initial momentum.
Equals mass times final minus initial,
Yeah.
right here.
It's a simple thing.
What is required to change the velocity of a bowling ball.
Can you think back as far as how did she do that? How did she make
What
them?
did I do? How did I do this? Well,
Don't hurt yourself. You changed the velocity.
I kicked it right with my foot.
Can you change the velocity again? Oh!
Okay, so what am I doing here? I am simply applying a force.
Oh, that's right.
Okay, I'm just applying a force. There it is. Right there. Okay, so what is required to change the velocity of a bowling ball? Applying a force. Momentum is changed by an applied net force. That makes sense because if I have to apply a force to change the velocity, well, momentum is mass times velocity.
Yeah.
Right? So it's making sense.
That sounds a little bit like Newton's laws, kind of, a little bit.
Momentum is changed by an applied net force. Football photo. Here we go. Look at that. What do you guys notice?
That football's got a dent in it.
This is actually regulation size football fully pumped up.
Whoa!
So it's not flat or anything.
How did they take that picture?
So this is actually a snapshot, like a little sliver or slice in time. There's stuff that happened before and stuff that happened after. We're freezing this frame right here. And this is a picture of if my hand is the football and the foot is coming in, okay, boop, 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 it's right there in the course of things.
What's going to happen is after the picture is taken,
Well, after the picture's taken, it might go one more, two more, and then the football is going to go
it's going to go flying off.
into
That's
the
right.
air. So we have the foot that is doing work on the ball.
Yeah.
Right, we're kicking the ball. It's going with a force, and it's going a certain displacement.
But
But also, we're putting a force on the ball, and what's going by?
Time goes by.
Time goes by. So it takes time to apply a force. Force applied in time is called an impulse.
Impulse.
So you just saw an impulse because the foot was applying a force, and at that very moment it was a sliver in time, but over that whole time, as that foot hit, it was applying an impulse.
Yeah. That force is applied over a time interval. All right.
Okay. Where's my mouse? There it is. Next slide. Okay. The area under a curve on a force versus time graph shows the impulse.
Huh.
Let's take a look at that. Okay, so here we are. That's this guy right here.
There's a force over time graph.
Yeah, so we've got force here, we've got time here, and you can see that this is happening over 2 seconds, and we exert a force of 5 newtons. And then over here, the same thing, but our force is negative.
Oh, that'd be like speeding it up, and the other one would be slowing it down.
Yeah, and so what it's telling us is that the area under this curve is the impulse.
So we can find the impulse by looking at it. I guess that's number 3 here, huh?
Yeah, should we do that one right now?
Let's do it right
Okay. So I can erase these ones.
now. Yeah. I'll read it while you're erasing. It says, a 7-kilogram bowling ball is rolling down the alley with a velocity of 2 meters per second. So let's start off.
There it is, right?
7 kilograms is the mass,
Okay.
and the velocity is 2 meters per second.
Okay.
Okay. Wait a minute. How can we find out how much momentum it's got?
Well, momentum is mass times velocity.
Yeah.
So 7 kilograms times 2 meters per second.
I don't think you need a calculator for that one.
Nah, Miss Moore's got this. Meters per second, or same thing as a Newton second, right?
Yeah.
That's a 14. Sorry. Okay. All right.
Okay, and then it says, for each impulse A and B, find the resulting speed and direction of the motion of the bowling ball. So let's just do A.
Okay. So it wants to know the impulse, you say?
Yeah, impulse J is force times time, and the force is positive 5, and it goes from 1 second to 2 seconds. How much time is between 1 and 2 seconds?
1.
I don't think you're gonna need a calculator for this one either.
5 Newton seconds. Okay.
So it's go along, it gets a kick in the same direction of 5 Newton seconds.
Oh, yeah.
How much momentum is it going to have after that kick, do you think?
Well, the total momentum is going to be 5 Newton seconds plus 14 Newton seconds, or 14 kilogram meters per second.
Yeah, that's the new momentum.
So 14 plus 5 is 19, or 19 kilogram meters per. I'm only doing this twice because that's something that I was confused about earlier.
Yeah.
So these are two of the same thing. I'm going to go with this from now on. Okay.
Okay, so then the question is, what's the speed of the bowling ball after this impulse? So we've got the momentum. How can we find the velocity?
Well, we want the velocity, and we know. Well, do we have that thing yet?
All we need is P is equal to mv.
Yeah. Okay, so P is equal to M times V. And we know that the momentum is this.
19.
And we know the mass is
7.
so we can just divide by the velocity. Oh, sorry. We can divide by the mass to get the velocity.
That's an easy switch.
Yeah. So velocity equals my momentum, which is 19 kilogram meters per second, over my mass, which was
7 kilograms.
7 kilograms. I will need to use my calculator for this part. Okay.
2 something, isn't it?
19 divided by 7, 2.71.
So it's going 2.71 meters per second. So impulse changes momentum, and I think there's a slide that
Oh, yeah. Our next
talks
one.
about that.
Okay, impulse momentum theorem. What did you just say, Mr. Boykin? You said impulse changes momentum?
I did.
Impulse, the change in impulse here changed our momentum here. Okay, so impulse momentum theorem, the impulse on an object, which is what we had over there, right?
Yeah.
Is equal to the change in the momentum it causes.
Yep.
Or, something else?
Yeah.
Or,
This says exactly the same thing, but in equation form.
it's almost easier to look at.
Yeah.
So J impulse equals the change in momentum. So impulse changes momentum.
What is impulse?
Impulse is the force times the change in time.
And when momentum changes, what changes?
Velocity changes.
So, you've got kind of like a little pyramid there.
Yeah. When in doubt, we start with this. Start building out.
Now, how could we make that look like Newton's second law? Newton's second law is force equals mass times acceleration. This has force and mass. Where could we get acceleration out of this?
Okay, I'm going to draw this over here.
Any ideas, boys and girls?
Well, let's figure out. So what I'm going to go ahead and do is I'm going to divide by delta T over here. These cancel. I've got force equals mass. Now, delta V over delta T.
Change in velocity over change in time. That's acceleration.
That is acceleration. Bada boom.
So the impulse momentum theorem is just a different way to say Newton's second
It's
law of
Newton's
motion.
law in disguise.
That's what I'm saying.
Newton was the bomb.com. Okay. So this is, down here it says page 204, number 2. Okay. The driver of the compact car, from above, suddenly applies the brakes harder for 2 seconds. As a result, the average force is that Newton, an average force of that many newtons is exerted on the car to slow it down.
Sketch the situation.
Sketch it out. Sketch it out.
So there's the car before.
Okay.
So then a negative impulse, the impulse would be in the opposite direction. Well, you got to put the J in before you put the car in.
Oh, yeah. So the J, so it's going to be a negative J right here, right?
Yeah.
The mass of the car is the same, right?
It doesn't change.
No change. Okay. And then what else? What is it asking for us again? Let's bring this over here.
It tells us how much force and how much time.
Okay, and the time was?
Time is 2 seconds.
2 seconds. Okay.
And the average force is 5,000 newtons.
Here we go. And then what are we trying to find here?
Well, we need to find the impulse.
The impulse. Okay. Well, force changes impulse, right?
Yeah.
Okay. And we know that force is...
Force times time changes impulse.
Force times time. Excuse
yeah,
me. Sorry.
It's just going to be 2 times 5,000
Yeah.
is the impulse.
So 2 seconds times 5,000 newtons. That's going to get me the impulse, which is
10,000 Newton
10,000
seconds.
Newton seconds. There we go.
And it's negative because it's in the opposite direction.
We're braking, right?
Yeah.
Okay.
See, the arrow up here is
That's
negative.
our negative impulse. And what I should have done right here is this right here first. Impulse changes momentum. This is impulse. My impulse is negative. Negative right there.
So that's going to
Negative.
slow the car down. And the question is, what is the change in momentum? That is the magnitude of the direction of the impulse on the car. Well, the change of momentum is equal to the impulse, which is the final minus the original. And then it says, what's the new momentum of the car? So before it had 20,155.
Yeah, before, what was it? 20,000. Show the one we got that, Mr. Wiggin. Over here,
That's what we
right?
did
This is my
earlier, yeah.
initial one right here.
Yeah.
Or Newton seconds here. So this is subtraction, which means I'm gonna add,
Yeah.
right? So I'll add 20,155 Newton seconds. And I'm gonna get my final momentum.
Hold up. There's something wrong here. Oh, no, you're right. No, you're right.
Good so far?
Yeah.
Okay.
So that's going to be negative 10,000 Newton seconds plus 2155. And I'm going to tell you, I don't need a calculator for that one.
At 20,155. You don't need a calculator for that?
10,155, right? Tell me it's 10,155.
It is 10,155. Do not feel bad if you could not do that in your head. 155 Newton seconds. Okay. So that means over here, our final momentum was 10,155 Newton seconds.
And the last thing it asks for is how fast is the car going? What's the velocity of the car now?
How fast is it going? So mass times velocity. Yeah. And we just divide by mass. Velocity is going to be 155 Newton seconds divided by the mass.
725 kilograms.
So 1055 divided by 725, and I get 14 meters per second. Does that number make sense?
It was going 27.8 meters per second before, and now it's going 14.8.
I mean, that makes sense. We put the brakes on, right?
Yep.
It's slowing down. Force changes momentum. Because we're changing the velocity here, mass stays the same, and we're going slower.
All right.
Okay.
I think it's time for the koosh ball.
You're right. The koosh.
Swear.
Okay.
Miss Moore's going to give it up.
Wait, let me go back here.
Yeah.
The koosh is for this one.
So
Okay.
what does it mean? Force times time changes momentum.
So what does a force over time look like? Is that our question?
Force over a time interval.
Over a time interval. Okay. So the projector.
You have a koosh ball and a
Koosh
golf
ball.
ball. They have the same mass.
Same mass, and if I throw them up, they're going to come back down. Whoops. Okay, at the same exact speed.
Yeah.
Okay. Therefore, same mass, same velocity, same momentum.
Same momentum.
Okay. So I drop. Oops. Okay. Same exact speed, same momentum.
Yep.
Okay. Now, how come when I throw this in? So I'm gonna throw this up in the air. I'm gonna hit off my head.
All right. Koosh ball.
Ah.
Whoa!
Not problematic.
Ouch!
Ouchie, that does hurt.
That made a doink sound.
Oh my goodness. So how come? Oh man, that does hurt. So
Imagine
how
doing that
come-
4 times a day.
Yikes. Oh my goodness. So how come the golf ball hurts if they have the same mass and the same velocity and therefore the same momentum?
Koosh ball, golf ball. What's different about these guys?
Well, okay, so we said that the impulse was a force over a time interval right here.
And impulse changes momentum.
Oh, change momentum, and they're both equal. They're both the same, right?
Yeah, and they both have the same mass. They both have the same change in momentum where they bounced off your head. But why did one hurt and the other one didn't?
Okay, so same. Let's take a look over here.
Where brings the pain, the force or the time?
The force,
Yep.
right? And so what happens is, as this koosh ball hits my head, can you see down there? It's kooshy, right? So when it comes in, it indents, and it takes a long amount of time.
Yep.
So it takes a large amount of time and exerts a very small force.
Didn't hurt at all.
No, it didn't hurt at all. It was unproblematic. However, this guy right here, there's no give.
There's no koosh.
There's no koosh.
It has no koosh.
And so when it hits me, it hits and bounces right off. Unlike this one, there's that delay koosh, the koosh.
Yep.
No koosh. Okay? So because there is no koosh, very small koosh here, it hits me with a big force.
Ouch.
Ouchie's right. Sadness more. Okay.
Mommy, don't do that.
Yeah, don't do it. So that is why the golf ball hurts, and you should not do what I did. Okay. So how does this apply to the real world? How does the koosh apply to the real world? So if you take a look at the way cars are designed, so some cars are built and they have this crumple zone in the front here.
Passenger cars are designed to crumple up in a crash.
Yeah, isn't that why the Volvos aren't they really good cars or?
Initially.
Yeah, initially, if they don't get kooshed. Okay, so what happens is this crumple zone allows for more time when the car gets hit.
Yep.
And that means that you're gonna get hit, you're gonna experience less force.
Yep.
Now with your brand new spanking new trucks, although very cute and very fun to drive, they are built with this ladder frame. And as you can see, they don't have that crumple zone that your 4-doors do. And so all they have is their bumper in the front that takes the impact and acts like a koosh.
Yeah.
And so over here, that because they don't have that crumple zone, it means that when another car hits you, it's going to hit you in a very short amount of time, giving you a lot more force.
Here's my car on October 10th. See the car in the background that's upside down? Guy ran a stoplight and we T-boned him. And the front of my car crumpled up like that. But notice, only the front of the car was damaged. The passenger compartment is fine. The door's still open and closed. And Mrs. Boykin and I survived because of the crumple zone. Yep.
Okay, the crumple zone gives you the koosh that you need to
And the
reduce
airbags,
force.
the airbags helped as well.
Yes, they did. Does this mean I don't want you to buy a truck? No, but it's to be considered. Okay, moving right along here. A 0.05 kilogram rocket uses a 5 Newton-second motor.
Kilograms are the units of mass. Newton seconds are the units of what?
Time.
And force. So that's...
Oh, Newton seconds. Sorry, yeah. Newton seconds are time and force. That's impulse.
Oh yeah, so we got the impulse, we got the mass.
Okay, we've got the impulse. We've got the mass. Impulse is what? 5 Newton seconds?
5 Newton seconds, and the mass is 0.050 kilograms. And the question is, how much momentum will the rocket have after the motor burns?
Okay, so it wants to know momentum.
So we'll assume that the rocket is sitting on the ground.
Chilling.
Yeah.
Okay, so we know that impulse changes momentum, and this is mass times
Well, we don't
velocity?
need... Yeah, we do. Okay, but we don't need that just yet. Let's make a pyramid.
Oh, yeah, okay. Sorry. Okay, how much momentum will the rocket have after it burns? So we can say
J equals delta P.
Yeah, delta P, there we go.
And so J is what?
Right here.
Force times, yeah, so that's force times times. That's going to be 5 Newton seconds.
Yeah, 5 Newton seconds.
And change of momentum is the final minus the original, isn't it?
Final minus initial. Well, the initial is going to be 0, right?
Yeah.
Okay, so this will be 0. It'll just go away. Okay, and the final is going to be mass times velocity, right?
Well, it's going to be...
Oh,
the
that's,
final
sorry,
is
that's how much momentum it has.
It's
Sorry.
going to have 5 Newton seconds.
This is way easier than we think it is, right? So the answer is...
How much momentum will it have? 5 Newton
5
seconds, or
Newton seconds.
5 kilograms, meters per
Yeah.
second.
Okay. So how much momentum will it have? Bada boom, the same exact amount. Impulse changes momentum to the same thing.
How fast will the rocket be going?
How fast, this is what I was thinking of, okay? How fast will it be going? So now we could think about how momentum equals mass times velocity. We divide by the mass.
It'll give us the velocity. So it's
Momentum was this.
5 Newton seconds divided by 0.050.
Bada boom. So 5 divided by 0.050 equals 100.
100 meters per second. That's pretty fast.
100 meters per second. All right, so when the rocket blasts off.
Pretty simple, pretty straightforward.
Okay, your homework.